So, hello everyone. I'm Boris Malashenko from ITMO University, and today I'll be presenting our review on leveraging large language models for scalable vector graphics processing. And let's briefly discuss what vector graphics are and how they differ from more common raster graphics. And unlike raster graphics, SVG rely on mathematical formulas. They represent images with formulas, and images are constructed from distinct elements like circles, rectangles, path elements, and for each image and for each element, different attributes can be applied, like color, stroke, and maybe more complex like gradient, and so. And why is it essential to use SVG graphics in design and other business applications? That's because they combine precision, flexibility, and cross-device applicability. And it's extremely useful to have resizable images, as they can be the process of editing can be easily automated. We can use different images. We can use one image on different devices, and user can change his preferences on the fly, and so on. These qualities make SVG an ideal format for modern, scalable, and interactive visual content. And there are plenty of methods we can denote as classic, but they all share some drawbacks, like slow generation time, complex outputs, and an ability of intuitive control. One of these methods is SVG Dreamer. It's based on diffusion, and we can see that for a simple query, generate the Great Wall of China, it returns extremely complex image with thousands of distinct path elements, and it can be used in real world applications, and these limitations make such approaches inefficient. That's why we can use large language models in this task. As we can see, all SVG images are basically just code in XML format. And we all know that large language models can easily process code. So let's more formally denote all tasks we can apply large language models to SVG. First is generation. Taking some text query, we want our model to return some SVG based on this query. Editing is changing some properties of our vector image, and understanding is extracting of overall meaning of our image, or once more distinct properties. And we can divide all our large language models based approaches into two groups. The first one is just general purpose LLMs, which we somehow adapt for vector tasks just by instructions and do not change architecture or other parts of the model. And the second group contains specialized models which were explicitly trained for SVG generation or understanding or editing tasks. And let's briefly describe all specialized models. The first one was Icon Shop, and it actually is pretty simple. It has pretty simple idea. Let's tokenize our SVG image by individual path elements, and then by individual tokens, and passing query tokens to our large language model. Here it's denoted as autoregressive transformer. Alongside with SVG tokens, we autoregressively predict next SVG token, which here is some pass command. The second work was actually pretty similar to the first, but here we have additional model called VQ stroke. On this image, you should look at the bottom side. And VQ stroke uses more complex tokenizations. It doesn't predefine, it doesn't use predefined tokenization algorithm. It learns during training how to tokenize an image. And then, once again, large language models autoregressively predicts next part of our image. The next work called star vector was more complex, as it proposed a multimodal approach in which we can pass a raster image or text instruction, one of these. And they both translated to tokens and then concatenated with SVG embeddings. And again, we autoregressively predict next token, so just like in previous works. And the most novel work is the method LLM for SVG proposed in the paper Empowering LLMs to Understand and Generate Complex Vector Graphics. And here authors introduce 55 special tokens with which they encode their input SVG query, input SVG string, and they train on not just on generation, but on 5 tasks, 4 of which understanding with different prompts. And they show that such multitask approach provide a significant quality increase. But the main idea here is the same. Let's apply some special tokenization and then just autoregressively predict next token. So to conclude, all methods share the same idea. As I said, just edit the tokenizer somehow and use LLM architecture as it is. So now let's discuss how to evaluate such models. And there are plenty of benchmarks, but we can't use just one. Let's discuss why. First, let's briefly observe each of those benchmarks. First is image text bridging. It consists, it focused on evaluating understanding of our model, and it has different levels of complexity tasks with kind of simple questions, but still those complexity can be still hard for some models. And the next benchmark is SVG Edit Bench. It as can be seen from its name, focused on editing, and it consists of 6 editing tasks, which are like the most basic editing that can be applied, like changing color, setting contour upside down, and so on. And here are 5 tasks. The 6th one is the hardest one. It's called compression. It can't be illustrated, but most models fall short in it. SVG taxonomy benchmark is focused on plots and diagrams only. It has a couple of different plot styles, from which we ask model to retrieve some numeric values, like mean of our plot or other key values. VG benchmark consists of 2 tasks, VGQA and VGen. VGQA is just like a quiz with 3 types of categories. We pass SVG image with the caption, with the query, and 4 answers, and ask it to retrieve the right one. And VGen is just we have a long prompt and ask our model to generate SVG image based on it, and then compare resulted image and ground truth via clip score. And the last one is SGP bench. It has the same idea as VGQA, but it doesn't limit it on 3 categories. It has a lot of categories, but we found it to be the most noisy one. As you can see, the second question, when we have a book illustrated, the right answer in dataset is newspaper. So there are some drawbacks in those datasets that should be observed. And why do we need aggregation? To evaluate all 3 tasks we previously discussed, we can't just rely on one benchmark. That's why we will use 3 of them: SVG bench, VG bench, and SGP bench. And here are our results. On those 3 benchmarks, we did evaluate a lot of different models. However, from specialized models group, it's group A, we was able to use icon shop only because it's the only model during our paper application which had open weights, but still, so we can see that as we predicted, DeepSeek Ardin R1, DeepSeek R1 shows superior results to other models. However, it's interesting that code editing model got strong, got extremely high score in editing. We believe that's because it trained this way to work with individual code elements. And let's observe some examples. We take the best model from each group and some random text prompts from VGen benchmark, and we can see that icon shop falls short, but we need to say that it can only generate black and white images, and all other images or all other models generate pretty same patterns, but DeepSeek R1, which is built on top of DeepSeek v3, it shows more stratified details and some examples of editing. We can see that DeepSeek R1 almost succeed almost everywhere, but in the last task, it didn't produce any compilable SVG at all. And let's see how reasoning helps, how reasoning enchants SVG processing. We can see that all reasoning models, we have one reasoning model actually, and the reason-based distillations overperform the common model, the models of the same size without reasoning. And to conclude, we reviewed 4 LLM-based approaches and 5 SVG benchmarks. We aggregated those benchmarks and evaluated 21 models and provided a clear comparison of model performance. And we believe that large language models are highly effective in SVG processing, but some limitations are still exists. And the future steps include enhancing current benchmarks as they have some noise, and explore tokenization more, and maybe explore architecture of models, because all current approaches just focus on tokenization, and build user-friendly tools to be able to effectively use such models. And thank you. That's all.
Thank you. Do we have questions from the audience, please? Seems to be not yet. I have a question. Maybe I have missed it on your talk. Sorry, but it seems to me that there were some classical approaches to the task you're describing. Something like the previous speaker has mentioned Sobel filter, and that's old computer vision stuff, and they seem to be having some effects still. Do you consider some hybrid approaches, not only using these large language models, but using also some classical approaches?
Actually, in this review, we did observe only approaches that rely on large language models, but we believe that classic approaches may be still useful, but the magic of large language models, we believe the future of this task is denoted by these models, because you can easily question the model by natural language. You can not just generate. You cannot just ask model for some properties of the image, but you can do that all simultaneously and have a great result, something like that. So,
okay, thank you.
So I believe it's just more useful in the future.
Yeah, of course. But large language models, you know, they are large, but the classical approaches are working even on, I don't know, the old fridge for nowadays. But still, thank you for the answer. Do we have? Yeah, we have questions from the audience, please.
Okay, thank you for your speech. Could you tell us, have you discovered some actual tools for SVG generation, maybe in Photoshop or something like this?
No, I believe we did some proprietary solutions, only some proprietary models, but I believe we don't know what's inside those Photoshop tool, so we don't consider that as approach we should focus.
Okay, thank you.
Thank you for your presentation. Could you please repeat what do you mean by reasoning? There was a slide with comparison the performance of the models, of the same models with reasoning and without. Yeah, so could you please repeat what the reasoning influence is? And did you study the impact?
Yeah, sure. So this plot just shows on y-axis the average accuracy over our aggregated framework, and we can see that reasoning is an special technique. How to tell it? In large language models was recently introduced. So we can see that models that somehow was trained with reasoning, they show superior performance to the models of the same size without such ability. But the reasoning is just the fine-tuning method when model somehow construct long thinking patterns inside and not just answer you implicitly like that.
Oh, thank you. I just thought that there was something in the prompt, but now it's clear. Thank you.